So let's get started, people. Before turn to the next topic, I didn't have time to discuss a couple things that are important when it comes to analyzing classifiers. And we've talked a lot about how to do an analysis of the results of classifiers and regressors. And I showed you these results the other day. And these results correspond to this algorithm that we saw here for the recognition of action units. Remember, action units, or AUs, are the results that you observe in an image given by the facial muscle movements that we can produce with the facial muscles that are under our skin. And I showed you how to model this with method like KSDA, kernel subclass discriminant. And I show you this video with some example, real-time example images. These are generally called qualitative results. Obviously, you want quantitative results as well, such as these ones. The question is, how are we going to provide quantitative results here, right? And what we talked about a couple lectures back is a way to do cross-validation, for example, on the end-to-end report, the cross-validation accuracy, right? And that's fair, but for problems like this, that doesn't work. And the reason is, okay, before I give it up, anyone wants to guess what the reason is? Why can't I use accuracy in cases like this? Okay.
You have bias in the data set?
There's bias in the data set, that's correct. But can you be more specific?
So if you have like 90% of the time with one class, you can get 90%.
That's a correct answer, right? Everyone heard this? So to repeat the answer, in many cases like this one, when you're trying, say, to detect here, action unit 4, right? What is the chance that you are activating the facial muscle movements that lower the inner corners of the brows right here, which is called AU4? It's very low, right? Most of the images will not have AU4. So if you design an algorithm that says AU4 is never active, right? It's never present, it'll be right probably about 90+% of the time. So the accuracy will be super high, but the algorithm will be useless, right? So this is a perfect way to lie to yourself and to your audience that you can do amazing things when in fact you can't. So how are we going to solve this? We're going to use other measures of accuracy to determine or to quantify how well a classifier does. So to show you this, let me go back to the definition of accuracy. This is the definition of accuracy. The definition of accuracy is how well you do, right, divided by the total population, the total number of samples that you have. Now, how well you do, right, the correct classifiers, the correct classified samples come from two parts. One is what's usually called the true positives, and the other one is what's called the true negative. All right, the true positive means the samples that correspond to the positive class, like AU active, right? And that I correctly classify as being active. The true negative are the ones that do not correspond to that class, like not having AU4 active, and I correctly classify as not being active, right? Not AU4 not being present, divided by the total population. Now, here you can see clearly if I mostly have negative samples, and I always say negative, then I'm correct most of the time, right? 90+% of the time. But we can define other ways to compute this, like this F beta score. And F beta is nothing else than a measure that computes what's called precision and recall. Now, precision is the fraction of samples in that class I that I'm interested in that are correctly classified, and recall is the number of correctly classified samples in class I over the actual number of samples in that class. Okay? So you can see it here in this nice drawing that I took from all places, I think from Wikipedia, if I remember correctly. It was a long time ago. Then they say Wikipedia is not useful. I may be wrong, but I think that's where it comes from. So imagine that these points here is your data set. And this half number of points is your negative samples, and here's your positive samples, and this is the classifier. And then let's say that this is your selection, and this is your true positives. This is then called your false negatives. This is your false positive, and these are called the true negative, okay? So this is what you classify as class 1. This is what you classify as class 2. And then here you are correct. Here, I'm sorry, here you are, no, wait, what did I say? Oh, this is the classifier, I say, right? So these are the false positive. No, this is wrong. All right, hold on. True positive and false positive. Okay, so this is your classifier, I see, okay? This is your classifier right here. So this part, this is the true positive because they happen to be on the side of your class. So that's correct. But this are from the other class, so you're misclassifying them. These are called false positives because you're classifying them as positive as being in your class, but they are not in your class, right? So false positives. Now, these are true negative, meaning these are the ones that you correctly classify as negative samples. But now these are called false negatives because you classify them as negative when in fact they are positive, right? So precision is nothing else than this portion of true positives that you have here, right, that you are selecting, so this part, divided by everything that you select, right? And recall would be this part here divided by all this part right here, okay? And this measurement now is an unbiased measurement with respect to the number of samples in each class. And that's what I was showing you here. This is in particular F1 score. Note that there is a beta here that determines, beta just determines how much relevance you give to precision versus recall, right? So you want to give more value to recall, you make beta smaller than 1. You want to make it precision more important, you make beta larger, right? So beta 1 is just basically you give the same value in both, right? So the precision and recall are equally good, and this is called F1 score, right? And now you can see that this algorithm might show you with KSDA for this particular problem in detecting, recognizing action units from images has an F1 score which is very close to 1, right? And 1 is the maximum you can ever have. So that means that this is a really good classifier for this class, right? But if I had shown you the accuracy I think that for this classifier is like 99%, right? But doesn't tell you the whole story, right? This does. So very important thing to know. An extension of all this that is a must for most two-class classification problems as we have been discussing recently. It's the receiver operating characteristic function or curve. It's usually just called ROC curve for short. And basically here is the hit rate, right, over the false alarm rate. So this here is how many times you make a mistake, right, the false alarm, and here's how correct you are, right? So if I have a curve that looks like this, right, that means that down here at 0, 0, right, this is, if this is the x-axis and this is the y-axis, this line would be x equals y, right? So then at this point, I never make a mistake, but I'm never right either, right? You see this? At this point here, 20% of the time I make mistakes, but 20% of the time I'm correct, right? So obviously this is random chance, right? This is the line of classification based on random chance. Anything that's above, it's good, right? Now, the perfect one would be a straight line over to 1 with 0 as recall, right? And then a straight line all the way here, right? If you can ever design a classifier like this, excellent. Most of the times, that's impossible, right? Because that would mean that the base error, remember, has to be 0, which is obviously rarely the case. But what you do want is to plot the curve of different algorithms, especially if you have different algorithms that you're considering, and select the curve that gives you, say, a larger area in between these two curves, right? Your curve and the curve that you obtain with random chance classification. Is that clear? ROC curves. This is very important. This is so commonly used in the literature, and not only in machine learning, all over science. You'll see ROC curves. They're very, very popular. Okay. Questions? All right. So let's move on. And as promised, we are changing gears to our last, very final topic in this lecture, which is deep learning, in this lecture, in this course. Okay. So, let's see where we are at. As we have seen thus far, there are in machine learning a large variety of algorithms that we can use, right? Let's see, if I'm interested in classification, I can use maybe the base linear classifier, assuming that I estimate my classes using Gaussian distributions. I can use linear discriminant analysis based on that classification. I can use a classifier like the perceptron, right? If I'm interested in regression, I can use what method do we see in regression? Logistic regression is a classifier. What other thing? Ridge regression, very good, right? So I could use ridge regression, which is the classical linear, simplest linear regressor that there is out there. Now, all this is very good, but we have shown that these methods only work if the data is linearly separable, right? Now, if the data is linearly separable, these methods that we introduced early on, they work great. I mean, absolutely fantastic. You don't have to, you don't have to use deep learning or any other more complicated method like mixture of Gaussians to estimate the underlying distribution of your data. If your data can be very well defined with a simple Gaussian or Laplacian or what have you, and a linear classifier will do. Why would you complicate your life, right? But the problem is that in most of the cases that we're interested in using deep learning, the data, the underlying distribution of the data is very complicated, right? Extremely complicated. And the data of different classes is non-linearly separable. I mean, let's face it. For the problems where it is going to be easily modeled with a Gaussian distribution or a Laplacian or any other parametric distribution, and the cases that are clearly linearly separable, those cases probably can just be implemented with a straightforward algorithm without the need of statistics and machine learning or pattern recognition, right? You just think about the problem, model the problem, and design an algorithm to solve it. The reason we use machine learning is because some problems, like a self-driving car, or the recognition of faces, right? Or recognizing a voice, right, in your phone, so the phone can write everything that you say in a text or email. All these things are very complicated. We don't know how to model this and write an algorithm. So what we want to do is collect as much data as we can, and then let these algorithms figure out how to solve the problem. That's what machine learning is all about, right? Give me the data, and I'll find you a mapping function, f of x equals y, where x is your input, y is your desirable output, right? So for example, x is your voice, y it's the text that transcribes what is being said in that speech. All right, so if we cannot use these methods and we need to use in parametric approaches, we need to use mixture of models. In non-parametric, we can use some method like k nearest neighbors, right? K-means. We can also use more complex classifiers, however, which are nothing else than the classifiers that we've seen, but we use a functional mapping that we called what? A kernel, very good, that maps or intrinsically maps our data x into a space of intrinsically higher dimensionality where my data is linearly separable, right? Now, of course, because this mapping is done intrinsically, and it's a Hilbert space, this is done with an inner product, then I can intrinsically map my data into a space of infinite dimensions, right? And if I have a space of infinite dimensions, then I can always find a hyperplane that divides my data. The problem is, how do I find that mapping, right? And we saw, for example, a method that I derived here on the board in our last lecture that optimizes homoscedasticity or spherical homoscedasticity, if you want to guarantee that the distributions, the parametric distributions of your underlying data are homoscedastic or spherical homoscedastic in the kernel space and are clearly separable with a hyperplane, right? So that's one way to do this. But how about if you don't want to use a parametric distribution, or you don't even want to estimate the underlying distribution of your data, right, in a direct way like this? Or your mapping function is so complicated that these methods do not work, okay? They don't have enough flexibility. We call this, remember, the VC dimension. You'll also see it being called the capacity of a classifier, right? Which is how much that function can deform to adapt to the, say in regression, to adapt to the data points, remember? For example, the degree of the polynomial that determines how much I can deform my manifold to adapt to the data samples that I have. And in classification, how I change the metric of my space, right? Such that I can map it into, intrinsically map it into another space where the data is linearly classifiable, right? All right, so all these methods are good, but still, it's still very difficult to determine the functional mapping. So this is what I want to find, how to determine that functional mapping phi of x that we were interested in. So and if you will, you can define this, from your space, say the real domain of p dimensions as per usual, to some kernel space F, right? So, for example, let's start. I'm just gonna introduce things very loosely first, okay? Then we'll get a little bit more formal, as we usually do. So let's start with our basic linear classifier, right? So I have, what do I have? I have y, my output, right? My desirable output is equal to phi of x, maybe given some parameters to this function, right? Like the Gaussian kernel or radial basis function that we saw, right? The logistic regression kernel and so on, right? Logistic sigmoidal function kernel. So, and then what am I missing here? So this is instead of x, right, to make it nonlinear, and then w, maybe w0, right, if there is an offset. I'm probably going to assume for now that this is 0 for simplicity, but note that there could be w0. You will also most commonly see in the deep learning literature a b here for the bias term. You know, it's same thing. Okay. So what's this equal to? This I can define as a functional mapping, right? From that has x, theta, and w as its parameters, right? You see that? So this function has now additional parameters, the theta parameters that define the kernel mapping, but also the w that define the hyperplane, right? And if you have the offset b, then b should be a parameter as well, right? Okay. So because we have this, like this, we can use regression to regress that function, right? So let's say that this function is in some hypothesis space, right? Remember H, our hypothesis space. This is the space of all possible functions that I'm allowing the function f to be drawn from, okay? It's not all the possible functions, but these functions that I allow to have. And of course, how big or how different I make this H will be what tells me or will be what allows my algorithm to find the correct solution or not, right? So this is the key to finding a good, I'm going to put good in quotation marks because remember what I mean by good in my particular problem under my assumptions and so on and so forth, my hypotheses. Key to finding a good solution, right, to my problem. Okay. All right. So I really don't know, right, in general, I really don't know what this H should be in general, right? As I showed you, you can derive this, the solutions for discriminant analysis and some others. But in general, I don't know. So what I want a large capacity, right, for my classifier or my regressor, which means that the BC dimensionality should be very large, okay? And, excuse me, one way to achieve this is to divide the problem into subproblems. So what I'm going to do, I'm going to take this functional mapping here, right? And I'm just going to say x and maybe some parameters here, okay? And I'm going to call it this 1. So this is the first function that I'm going to draw from this hypothesis space, okay? So far, so good. And so let's call these parameters maybe theta 1. And when I get this result, this is nothing else than a classifier like this, right? Instead of equaling this to y, what I'm going to do, I'm going to apply another functional mapping, say 2, with some other set of parameters, right? You see this? So first, in classification, I may change the metric, or in regression, I may find some manifold that adapts to my data. And then from here, I apply another functional that gets me even closer to what I need. But why stop there? How about if I apply a third function? OK. How about if I apply even more functions, right? So here at the end, I'm going to have f of, say, k, theta k. OK? And I can make k as large as I want to. And because you see how this is going deeper and deeper and deeper and deeper into functional mappings. It's a functional mapping over functional mapping over. This is why this is called deep learning. Yep, makes sense? OK. Now, the questions, so we're going to have to solve a few problems here. We have all the tools already that we need to solve this, right? We have derived all the algorithms that are necessary to do this already. But we just need to put everything together. The first thing is the first of the problems that we need to solve is how we're going to define each of these fj's or fi's, right? How are we going to define them? We could use known kernel mappings like the RBF or radial basis function mapping, or the sigmoidal, the logistic sigmoidal, the 10H, right? Remember 10H that I also introduced, and so on. True, but the problem is when these things are so big, it starts to become overwhelming, right? I mean, I cannot just keep putting things together at random and hope for the best. So I need to find a way to describe this. Did we introduce an approach that allows me to visualize these functional mappings? What? A graph, right? Very good. In particular, in general, deep learning in general, not always, but almost always, uses a direct acyclic graph to represent this, right? So what we're going to do is we're going to represent, say, the first function f1 as some sort of graph here. And I'll talk more in detail why I only have these nodes. But if you will, for now, you could have more than one node. OK, it's fine. So maybe here's x, right? And x is the input to a certain number of nodes. And maybe there are some connections here that go like this. Who knows, right? That define my f1, right? And once I'm done with this, I have constructed this graph. Then I have another graph, right? That this time maybe looks something like this. Whoops. And there are now connections, right, between, meaning edges, between this function and that function depending on how these functions share information, right? And this would be f2, which is the function that applies on f1, and so on, up to, some final number of nodes and edges that'll be coming from other places. And here I have my output y. Okay? And this out here will be fk. So far, so good? Okay. Now, this, as I said, in general, is going to be a directed acyclic graph, meaning you're not going to see this, right? That's not possible in a directed acyclic graph. And it's also a weighted graph. So this is a weighted directed acyclic graph, which means that you have weights here, right? And so on. Now, this resulting graph, this thing that you see here, the whole graph, looks pretty much like a network, right? So I have some nodes that send information. You can think about a device that receives and transmits information, right? So each node receives information and sends information to some other places. That looks pretty much like a network, like the graphs that we've designed earlier. Remember when we talked especially about hidden Markov models that I mentioned their importance in communications, right? The Viterbi algorithm and so on. So in general, this is called a network. Now, if you want to stretch your imagination, you could claim that these nodes represent or are equivalent to neurons in the brain of any animal, and that the connections in the neurons in the brain are called synapses, or the axons that have synapses to other cells. That these axons and synapses are defined by the edges, okay? And if you take that view, then you can call this a neural network, meaning that you are modeling a representation of and I must say, a feed-forward, right? Because it only goes in that single direction because this is a directed acyclic graph. So this is called, in fact, a feed-forward neural network. Okay. Now, of course, the brain, especially the human brain, is massively not acyclic. We actually have, for the visual cortex, for example, we actually have more axons going in that direction than going in this direction. Now, if you remember from image processing, and for those of you that have taken computer vision, definitely will know that what the information that we receive through our eyes is very limited and very ambiguous, right? First off, for every image that I observe, there's an infinite number of possible interpretations, right? And even in that case, the amount of information that I receive is not enough for me to interpret the whole world. So the brain has to have models of what my world is like, and then these models have to be sent down, okay, to the early parts of the visual cortex to be able to, for those areas, to analyze what we are observing, what we see, right? So remember, for example, the fact that you have a blind spot in the retina that you're not aware of because the brain fills in the information for that spot. The fact that you only have color perception at the very center of the retina. All your peripheral vision that you have right here is actually in grayscale, black and white, right? But you think it's colored, right? You see everything colored, but it's a lie, right? Your brain is lying to you. I mean, it's not lying to you, it's helping, right? It's just telling you, okay, that's what's most likely. That's how I estimate that the world looks like, right? But sometimes we're wrong, and that's why we make terrible mistakes sometimes, and so on and so forth. So if you only model the feed-forward component of the real neural network that we have in our brains, then that could be theoretically modeled at some degree with a directed acyclic graph like this. And as I said, there are some models in deep learning that do allow for feed-backward connections, okay? But that's very rare, at least right now. Topic under research, hopefully, will advance soon. All right, so you will see these things called, and all these terms are interchangeably. You'll see this called deep learning because of this fact. You will see them called neural networks because of what I've described here. You will see them called, although these days is not as common, it used to be more common, feed-forward neural networks is also another name that you'll see. You may also see just a net, right? For short, neural net, obviously, and you can also see deep networks or deep nets, it's another, or deep neural networks. All these combinations are used. They all mean one and the same, okay? All right, so the way we define this this embedding of functions here is by coming up here, drawing, actually physically drawing a graph, right? And that way, because we are controlling the design of the graph, we can say, all right, if I have a sound wave here, right, that I want to analyze, then I want this part of the function to analyze high frequencies, right? And this part here, mid frequencies, and this one, low frequencies, what have you, right? And I want these first components, I don't know, maybe these first components here to analyze the whole section as a whole. But these other components here, I want to analyze the smaller sections, right, of the sound wave, and so on, right? So you can actually relate the physics of what you want to model with what you are designing, right? So you have some control over how you define these functions. And this is key, because otherwise deep learning would never work. I mean, it's not that you just come up with random functions here and you make it learn and it will learn anything, right? The question is, how are you going to design this? Now, I have to say that we still don't really know how to design these things, right? First of all, they are super massive. And what we do know is basically it has come out to us by trial and error, right? People have been trying things. The things that don't work, people don't publish. So unfortunately, we don't know what doesn't work. But things that do work, people do publish, and that's what we know that works for specific problems, right? I will talk more about this later. I would say not only for specific problems, but for specific data sets. Now remember when we discussed what was this? When we talk about this, I think might have been in the comparing classifiers lecture a couple lectures back. Maybe I'm wrong, but I did say at some point that there is not only the problem of overfitting to the training data, but there's a problem of overfitting to the testing data. And the reason is because your testing data usually is visible to you, right? So you keep modifying your algorithm over and over and over again until it works for your testing data. So years ago, a good friend of mine was running these face recognition competitions, okay? And that was in the early 2000s. And the way he would do that, he would create a database, and he would give you the training data and some verification data for you to use, and he would sequester the testing data, right? So the testing data sequestered, you have never seen it. So you design your algorithm on the training and verification data, and then when the day of the competition, you submit your algorithm to him or to a server, and then it runs on the testing data, the sequestered testing data, and you get some result. And it was very funny because at the first year that the competition would run with this data set, the algorithms were at about, I don't know, 30% accuracy, whatever it was, right? I forget the exact number, but about 30%. It was very low. And then the second year, people were about 60%. You know, people had improved their algorithms. I mean, they had learned that there were things that were not working. And a few years later, they would be at the 90+%, right? And some algorithms may actually even reach 98, 99%. So why would that happen? Well, because people were adapting their algorithms to that specific data set, right? But my friend would not be deterred, and every few years he would come up with another data set, right? So the competition would continue, but the data set would change. And then the year that the data set changed, all the algorithms went back to 30%. And that sinusoidal function kept going on forever until the competition stopped, right? And the problem is that it gets to a point that you know so much about that data set that you're adapting everything that we see here to your particular data set, right? This happened recently for object recognition. There are two huge data sets that people have been using in recent years. More than two, but two that were most popular, or three that were very popular: Pascal VOC, ImageNet, and COCO. And there were three different competitions for each of them. And I asked a master's student, one of you a few years ago, that was here in class and wanted to do something on this. And I just said, yeah, just take the algorithm, the deep network algorithm that someone designed to win the competition this year in ImageNet, and apply to COCO, right? And vice versa. Take the COCO winner and apply to, and obviously they would perform poorly on the other data set. It wouldn't be terrible, right? But it would not beat the best network or the best algorithm on the other data set, right? So you have to be very cognizant of these facts. Google found this probably the very wrong way because they designed an algorithm that could perform really well on ImageNet. So they decided that, that was a few years ago, they decided that the algorithm was working. And I kept telling my friends, all my friends, it's like, don't make these things public because these algorithms work on this data set. And these data sets these days, they're huge, right? They have millions of data points. They're really good. But millions of data points is not billions of data points or queries that people will produce on a page like Google or some other software that you may design, right? You don't know what people out there are going to do with your system. So what happened is that, no, they would not be deterred, these researchers, so they convinced someone at higher up in the hierarchy, I guess, to make this available. And I forget the details of how it was made available, but there was a page within Google where you could go and submit an image, okay? And it would tell what objects that image included. Fascinating. First day, I mean, within hours, I think, of the system going up, a reporter from maybe the Washington Post, you can Google this and find out where, went online and submitted a picture of, I don't know if it was him, a friend, of an image that he found online of some African American person, and the system returned gorilla as the outcome. Now, as you can imagine, he went white, like I'm probably white now myself, just thinking about it, and wrote an article about this, posted it online on the Washington Post page, webpage, and that site went off like in minutes, right? That Google site. I mean, it went off. It's never been on again. That tells you how careful you need to be, right? When you design these things and test these things on very limited, even if it's millions, very limited data sets. You have to be very careful. I mean, think about what Google has been doing with their self-driving car. They have had the self-driving car for how many years now? I can buy it, why not? They don't trust it, right? The day that it's ready, they keep saying, when is it going to be for sale? They ask them, and they say, when it's ready, right? And the thing is, when are you comfortable enough that you think, yeah, I think it's going to work? Apple, just to talk about another company, Apple had this Face ID, right? And there are actually former students of mine that work there in this group. And this is a fascinating algorithm. It works really well, right? I mean, they've done an amazing job. It's just one of the best products that you'll find out there. One day I was on YouTube and there was this recommendation, random recommendations that YouTube gives me. And I guess that because I'm a face recognition guy that it recommended this thing. It was a 10-year-old or maybe an 8-year-old that could unlock his mother's phone with his face. Now explain that, Well, there's 7 billion people on Earth, right? You're not guaranteed to make it work for 7 billion people. It's the degree of complexity in the real world compared to your database. Doesn't matter how big your database is, it's always going to be much larger, right? So these things are real, and you have to be cognizant of that, and you have to be very careful on how you design these things, and most importantly, how you interpret them, okay? Now, having said that, deep learning is a really powerful tool that works really well for some problems, okay? Speech recognition, translation from one language to another. It was really funny. A few years ago, the translations were so bad. There were these high school kids. Have you guys seen this? It's really cool. They're probably still online. I don't know. Some of them were deleted because obviously companies didn't want this to be out. But what you do is that you take the text of a song or of a poem or something, right? And they translate it, say, from English to Mandarin Chinese, from Mandarin Chinese to Spanish, from Spanish to, Korean, from Korean to French, from French to something else, and at some point they would go back to English, right? And then they would go in front of a camera, they film themselves either reading that result, the poem, or singing the song, right? And it was so funny. I mean, you have to give it to them. They are so creative, the skits. It was amazing. So Yeah, it was really bad. The translations were really bad, especially if you did a few in sequence, right? Now they're not great, but they're much better. If you've tested the translation systems in recent months, they work really well. I mean, obviously, there are these errors that are very hard to solve. It's raining cats and dogs or what have you. Obviously, there's things that are very difficult to translate. But in general, they work really well. So to the point that I think at least you can understand what the contents of what you are reading in another language are, which is a huge improvement. Speech recognition, I used to, speech recognition has been around forever, and I used to be very annoyed by it, especially over the phone. I remember once that in one of my trips, my luggage got lost or stranded somewhere, and I had to call the airline, and I called them, and it was an automated system that was years ago, and said the system said or asked me, what was your city of destination? And I was like, and the system goes like, Houston, Texas. Like, what? How is similar to Houston, Texas? I have no idea, right? But that's how bad systems were. Now they're pretty good, right? I don't text anymore on my phone. I always speak to my phone, and it works. Maybe it works 99.9% of the time. Yeah, there is a few times where it makes a mistake, especially if I'm texting a student and I'm talking about technical stuff. But in general, it's pretty good, right? Face recognition. Face recognition has improved tremendously, and all these things are in big part due to deep learning, right? Now, remember what I always say. Machine learning in general, not only deep learning, machine learning is based on data, right? I mean, this is so important that I'm gonna write it big here. Data, right? Machine learning is based on data. So you have a data set or database, right? And ideally, if you can have big data, much better, right? Big data, lots and lots and lots of data. That's what machine learning is good at. But what do I always say about data? Data by itself is, what's that? Well, intrinsically damn, right? It doesn't know anything. It's not intelligent, right? It's stupid, basically, right? Data doesn't know anything. So the machine learning algorithm that you use, it's going to learn whatever thing, good or bad, that your data has. Why did the Google system say gorilla for a human face? I mean, this is serious. This is very serious. Well, who knows what happened, right? But one of the problems is maybe none of the engineers that designed that system thought, maybe we should include African Americans in our database. And that's a problem. Diversity is important, right? When you don't have diversity in your group of engineers, these problems occur, right? And I remember that was many years ago that some group found that if you Google woman CEO in images, Google Images, the first result was Barbie CEO, right? Which again, why? Because probably at that time there were no women working in that group, or very few, and no one had thought about, maybe I should try that keyword, right? There is a huge area of research right now, and this is still in research, but it's a huge area that is trying to address this bias issue, okay? People have already shown that most, if not all, the face recognition systems that are out there are racist, right? It's this graduate student at MIT that had this paper that she wrote. She says, because she was trying these systems and the systems would not detect her face. I'm like, I'm right here. But if she would put a mask, a white mask or whatever colorful mask, then she would be detected. Oh, it just happened to be black, right? If you don't have people like this in your group, you're never going to test these things, or it may not occur to you to test these things. And then the systems are racist or sexist or Nazis, right? Microsoft, to talk about another company, I think it was Microsoft, that wanted to design this chatbot that learned from interactions that people had. So they opened this platform where people could interact with one another, right? And the system would learn what it means to interact with other people. But some people out there outsmarted Microsoft, and they started communicating with xenophobic and racist terms. And they were just basically Nazis, right? The way they were interacting, at least. And what did the system learn? It became a Nazi. Yeah, that's the data it was given. It's not that the system was by design a Nazi, it's that the data intrinsically is dumb. The data doesn't know anything. The data is whatever you give it to the system. So super careful with what you give. That's the problem with self-driving cars, isn't it? It's not that companies don't think that their systems work. Their system works really well. But have we accounted for everything that can happen? Of course not. And that's impossible to begin with, right? It's impossible to account for all the possible zillions of things that could happen to a car. But the question is not how big can I make my database, but how do I know how my algorithm will respond when these previously unpredicted, unseen conditions occur, right? And that's another huge area of research, right? There is research in trying to provide interpretability, explainability of what these huge systems like deep networks or complicated kernel mappings do. How do they accomplish what they do, and why do they work, and why do they fail? Understanding this, we don't understand this right now, but if we could understand this, that would solve a lot of problems. Then we could address all these issues, okay? But keep in mind that at this point, the best we can do is design really good data sets. Okay, so let's probably, let's probably get started with, I'm probably gonna skip this. Let's probably get started with a more formal definition of all these things. And I hope to first go back to all the things that we already know and review them as they apply to deep learning. And then I'll talk about the specific architectures of these networks that are known to work for a variety of problems. And then hopefully we will have time to talk about a very exciting new area in deep networks, which relates to unsupervised learning. So remember, this is still all supervised. So it will be either semi-supervised or unsupervised. We'll talk about this. And also transfer learning if we have time. Okay. So there are two things that we need to address. One is how to design these networks, okay, the so-called architecture of these networks. So this would be the graphs. And the other is how we're going to learn. And in particular, we're going to talk about a an algorithm, which is nothing else than we're going to use nonlinear least squares to give it up. And in particular, we're going to talk about backpropagation. Now, backpropagation means that I propagate. So what I'm going to do, I'm going to use an input here, x, let's say xi, and xi corresponds to yi, right? But the network is going to estimate yi hat, say, right? And then I'm going to use a loss function to compare yi with yi hat, as I always do. And then that error, I'm going to backpropagate it through the network. And by backpropagation means that I'm going to change the parameters, like the weights that I have here in my edges in this graph, such that next time I use that input, I get closer to the true output that I want. Okay? And as we know, this can be solved with nonlinear least squares, meaning I take the derivatives, right, of the loss function. If it's the square loss, right, I take it's least squares. I take the derivative of that, and then I equal this to 0, right, and I go one by one. But the problem now is that I have an embedding of functions, right? So I'm going to start at the last one, and I'm going to take the partial derivative of this, and then I have to take the partial derivative of this, and then the partial derivative of this, and so on, right? And that's what's called backpropagation. All right, so we'll talk about these two things. So you'll see this notation that I have given here, or maybe that other notation, S of f of x. Now, S here is not the output, but it's the output, the intermediate output at some stage. So more generally, obviously, you'll have S equals f of x theta, where theta are the parameters of your function. As I just said, we need a loss function right here, right? We need a loss that we want to maximize or minimize. So, for example, we could use the hinge loss, right, as an example. You could modify the hinge loss for these networks. So, for example, you would end up with a loss function for the ith sample that is equal to you sum over all the j's that are different than your output yi, right? And then you do remember the hinge loss is either 0 or that linear function that we derive, which in our case would be sj minus si, right, for yi, plus 1, right? And so on, right? You can use whatever loss that you want. And we'll talk a lot about the loss function because once we remember that we need to talk about these two things, right? And this is going to be related also to the loss function. So one thing is how we define the architecture of our graph or our network, and the other one is how we learn. And the loss function has a huge weight on how these things learn, right? Depending on what I want to learn, I'm going to use one loss function or another, right? And the design of the loss function is the most probably important part of the network. Because the network, you're probably typically just going to use some architecture that is given, right? That someone has shown that it sort of works in a variety of problems. Okay, so with a given loss, we can derive now a regression criterion. So we now derive from that loss a regression criterion. So for example, I could have, say, I sum over from 1 through n all my LIs here that I have here, my losses for all the samples, right? I normalize this 1 over n. And maybe what I'm going to do, I'm going to add a regularizer, right, to make this function a little bit more stable, remember, for the computations. So I'm going to regularize this. So I'm going to add, say, wk square, k1 through m as a regularizing term to make the computations more stable. All right, so remember, if I want to find a solution for this, what do I want? I want to, say, minimize or maximize my function L, which means that I need to take the derivatives, right, the gradient with respect to my parameters, say W, for example, of L, right? And then that the derivative tell me in what direction I want to go, right? So remember, if I have here the gradient of my function, right? And my function looks something like this. And I start, say, over here, then the gradient is telling me that there is a minimum in this direction, right? And that's what I want to do. So this would be the normal. This is the gradient, which is orthogonal to it. And then I can use the Jacobian matrix and the Hessian matrix, right, to know how fast I need to go in that direction to get as close as possible to that minimum, right? And if I started here, it would give me this direction, which allowed me to find this minimum and so on. Okay. Now, I do want to say that there are two ways to do this in these deep networks. One way is to derive the gradient analytically, excuse me, which is what we have done in this course. I think that's the correct way, okay? If you can do it analytically, it's just so much better. But you could do that numerically as well. That's fine. I still prefer that you do it analytically, at least if you can. But there is something that you could do. You could run once you have done your analytic, once you have computed your analytic function, right, your analytic derivations, excuse me, you could then run a numerical computation, right, and verify for some particular values in your analytical function, right, that is exactly the correct solution, right, that both the analytical and the numerical approximation gives you the same solution. So maybe as a test of a test step to make sure that you did the right thing, that's fine. But in general, we'll be working with the analytical derivations. All right. So remember that we use these directed acyclic graphs to represent this. You'll see these sometimes called computational graphs, meaning that we can represent our function f of x as a graph. And for example, let's say that I have f equals wx, right? Our basic base classifier that we keep going back to. Well, for the base classifier, I'm missing the bias, but assuming the bias is 0. And that means that I can represent this as a graph, say with x, w, right? Then I do a product here. So I compute the product of these two, the inner product, say, right, of these two variables. And then that gives me S, right, my output, or F. Or actually to get, well, sure, let's call this F. And then I apply here a loss function, right? And now for this loss function, I combine this with, say, my weights, right? And I output some result that I can now use to modify the original weights. Now, of course, these graphs can get very complicated very quickly. So here I'm only able to give you a very simple example. So why don't I give you, let's see, let's do this. We'll work out an equation and its corresponding graph right here. And then at home, you can do the derivations for to compute the gradient, right, the partial derivatives. And then we'll give the solution in our next lecture. Let's do that. So, okay, how about if I do, what am I going to do? Maybe xy plus, or I know what I did. Let's say f of x, y, z. I'm going to use 3 variables. Maybe I can do x, y plus z. How about that? Right? If you want 2 options, maybe another option, so it's called this f1, f2, could be x plus y, and then multiply this by z, for example, right? Whatever it is. So that means that I have x, y, and z. That's my input. And now I combine these 2, and I do a product. And then I combine these 2, and I do an addition, right? So this is the node here. That's an addition. The weights here are just 1, right? And that's my output, right? F. Now note that I could also write x, y, z. Maybe let me do this other one now. I'm going to do plus here. And now note that I could also do, for symmetry, I could do this one with this one, and this one with this one, right? You see? So they all add with each other, right? But now I can assign weights, right? And I can say, all right, this and this add together, but this and this do not, and this do not, right? I could also do that, right? And then I could say, now I multiply this result by z, so I have the z product here. And again, I could do this with everything else. I could say, oops, not this one, excuse me. I could say, now I can take this summing term, which is x and z, and multiplied with y. And I can take this one, which is yz, and multiply by x, right? And I get these other ones. And again, I can assign a 0 weight to just the output of this. Well, in fact, I probably wouldn't need to do that because this is already 0, right? So this is just going to be 0 at the output. And that's it, right? That function now here, let's say if I have these different products, I can now combine them with a plus, right? And now this function is f2. You see that? See how this works? So you can come up with different graphs that represents these different functions that you may want to work with, right? So if you want to work with one of these, right, what do you need to do? Well, you need to compute the partial derivatives, right? So if this is the first term that we compute here, right? See that first term, that first node that computes this product? Well, say I call these, I don't know, P, or I use P, so Q. If I call this Q, right, then I can compute the partial derivative of Q with respect to x, right? And let's see, I can also compute the partial derivative of Q with respect to y, right? So what would this be equal to, anyone? And this one? Very good, right? And now what do we have? Now we have S, our output, or F1 rather. F1, our output, is equal to Q plus Z, right? So now I want to do the partial derivative of F1 with respect to Q, and the partial derivative of F1 with respect to Z, right? What's this first one equal to? One, okay. And this one? One, very good, right? So you see how this works. So do at home the other one for this one, right? X plus y times z. Just practice these things. So this is how you can compute the different partial derivative. Now, if I want to get this one, this is the partial derivative of f1 with respect to the output variable y, then what am I going to do? I'm going to apply the chain rule. Very good. So I can do the partial derivative of f1 with respect to, wait, what did I say? Let me not call this, I did something stupid here. Okay. Let me call this S. I see why I call this S. My bad. So this would be now the partial derivative of S, right, with respect to Q times the partial derivative of S, of Q with respect to Y, right? And now you can solve it and find the solutions, right? Okay, do this one at home, and we'll do this in our next lecture to make sure that we understand how to apply the chain rule. This is just the chain rule. I mean, it's nothing novel. But yes, question. Complex numbers?
Yeah, because the derivative of complex function will be much better.
Right. So the short answer is yes. The long answer is complicated. Yeah, you're correct. The details of how to work this out are not as simple. Yeah. Any other questions? All right. I'll see you Thursday.